All right, I'll go ahead and get started then. Thanks for showing up to my talk. My name is Taylor Patterson. I'm a developer on the Eclipse ICE project. I work at Oak Ridge National Lab where Eclipse ICE is primarily developed. And today I'll be talking less on our development and more on the work that we've done to incorporate usability testing into our software development processes and how we've used usability testing to improve the user interface quality. There we go. All right. So look at where we're headed over the next half hour or so. I'll first start out with a discussion of why we decided to do usability testing and what really motivated us to do this and bring it into our software development process. And then I'll provide a brief overview of the product that we were testing with. So I'll provide you with some background information about Eclipse ICE. And then I'll start to dive into the details of our design, planning, and execution of our usability testing. And when I get into these sections, I'll kind of go through a sort of how-to approach and discuss the steps that we took, and then sort of do it as a case study and how we applied those steps to our case, and then incorporate some of the software and hardware tools that we used along the way in order to help us carry this out. A quick disclaimer about the way that we did this. Generally, usability testing or usability studies, usability testing is a very fluid process. And you might have people use your software, get immediate feedback, and make immediate changes to your software. The way that we decided to do it was to take a more traditional cognitive science research approach to it. So we took a very controlled approach. And although our approach might not be typical for the usability testing community, the steps that we took can certainly help to get you started, however whichever path you would choose to take. After getting through the planning, design, and execution, then I'll finish up with a few of the outcomes that we've had or the results that how we've been able to use this. So first, why did we decide to do usability testing? And for us, it kind of started with the fact that we just felt that now was the time. The project had been under active development, not as an Eclipse project, but starting back just as an open source project of our own before joining the community about 6 or 7 years ago. And we felt that the code base had reached an appropriate maturity that now is the time that we should start to get more user feedback on this and see how we compare against some of the tools that we seek to provide an alternative to. Another motivating factor is that we just strive to create great software products. If we can't create a product that people want to use, they're probably not going to use it. So actually having these people do this allows us to also collect an abundance of data. We get to see people actually using our software and providing direct feedback in both indirect and direct ways, both through the responses that they give in questionnaires, as well as just seeing them use it and seeing where they run into problems and where the confusion is and why they're moving their mouse all over the screen trying to find something. As I mentioned, we kind of took a unique approach, and in doing so, taking this formal research approach, we wanted to publish on this. We wanted to talk about it. In my abstract or my proposal for this session, I pointed to two citations there of sort of opinions that usability testing doesn't normally get talked about, and especially in the open source community, it tends to be that way. The citations that I had were roughly 10 years old. They're a bit dated, but nothing's changed in those 10 years. Or at least for the most part, things haven't changed. The software product that we tested is, as I mentioned, Eclipse ICE, the Eclipse Integrated Computational Environment, which is a fully integrated workbench for scientific modeling and simulation. It allows users to modify simulation input, excuse me, launch jobs which may be on remote machines, and then pull that data back and analyze that data. It allows the user to do this stuff without any deep knowledge of those input files or of the launch configuration that they need. Traditionally, these tasks are done with command line tools or some other disjoint visualization tools. And Eclipse ICE brings them all into one place and allows the user to complete the entire workflow for their scientific simulations, all within a Eclipse IDE type environment. So moving on to our design and planning and what we did for this study, our method started with formulating a research question. Sure, we want to look at usability. We want to ask, how usable is our software, or is our software usable? But that's not really concrete. We need something, we need to think in terms of things that are measurable. And a good place to start for that is to ask a question of the form, how does X affect Y under some optional set of conditions? So applying this research question approach to ICE, we came up with two questions. We said, how does the use of Eclipse ICE affect user efficiency and success in completing a typical series of a typical series of scientific simulation tasks? And also, not a little bit, not quite to the same template, same XYZ template that we had, was how will users evaluate the usability of Eclipse ICE as compared to the use of alternative tools? Since a clear alternative existed for ICE, we wanted to see how we compared against those. After asking our question, then we can start to identify the variables in that question. We identify both our independent variables, which from the name you can guess are variables that depend on that their variation depends on other variables, or dependent variables, those that, sorry, I think I messed that up. Independent variables don't depend on the variation of other variables, whereas dependent depend on those other variables. Alternatively, we can use the terms factors and response variables, and those are the terms that we'll proceed with here. So after classifying our variables, then we start to identify relationships between them. And taking a more fine-grained approach to this, we say that the different values that our factors can take on are the levels, which can be one or several. And then we identify the relationships that each of those factors has on our response variables as an effect. So for our usability testing, recall our research question of how does the use of Eclipse ICE affect user efficiency and success in completing a series of scientific simulation tasks? So from this question, we can identify that our factor is the use of Eclipse ICE. And we have one factor in this question and two levels for it. Completing the simulation tasks with ICE or completing the tasks with the alternative tools. Also identified in this question is our response variable, of which we also have two, but I've just grouped them into the diagram in one place. And that's user efficiency and user success. So after identifying the levels of our factors and our response variables, we can start to postulate how do our levels affect our response variables. And based on our question, we say using Eclipse ICE is going to increase user efficiency and success. Or using the alternative tools, not using ICE, will decrease the chances of users being successful in completing the tasks and completing them in a timely manner. Recall we had two questions, and as I mentioned, this one doesn't necessarily fit the XYZ template that we had before, but we can still pull factors and response variables out of it. Again, the factor pretty much stays the same. It's using ICE or using alternative tools. And here, our response variable is how users evaluate the usability. So I guess now if we split efficiency and success separately, then we end up with three of these factor, effect, response diagrams, which will be useful in the next step, where we generate our hypotheses, which we consider sort of an interim answer to our research questions. And as a start for creating those answers, we sort of take our how does X affect Y under Z conditions and sort of reformulate that into an answer and say that X affects Y in W ways under those conditions. Our hypotheses also give us a chance to introduce interactions between factors. If we have multiple factors, we can start to provide answers as to how those factors interact with each other. So if we, considering our hypotheses, we go back to those convenient diagrams that we came up with and just call these hypothesis 1, hypothesis 2, and hypothesis 3. And taking the diagrams and using our X, Y, W, Z template that I mentioned previously for generating hypotheses, we can formulate these into well-formed answers to our questions. And we say, users of Eclipse ICE will be more efficient in completing each milestone in a series of simulation tasks as compared to users of the collection of alternative tools. Users will be more successful, and users will find that using Eclipse ICE is more usable, users of Eclipse ICE will find it more usable than the alternative tools. So the next step in determining how we design and plan our experiment is to consider our options for complexity and how participants are exposed to the different factors. In the simple case of traditional usability testing, you're testing essentially one piece of software and just seeing how they do that. You have one factor there. There's essentially no levels. They're just using that software, and so that makes this step trivial. But since our case was a bit different, we have to go through this step. And so our options first for experimental complexity. We could complete just a simple experiment, or we could use a simple design or a factorial design. In a simple design, we vary one factor at a time and study its effects. In a factorial design, you'll vary multiple factors at a time, and that gives you a chance to study their interactions. If you only have one factor, again, this step is trivial. If you have multiple factors but still choose to do the simple design, you do run the risk of ignoring those interactions. So you can certainly run into issues there and produce misleading results. But with two or more factors, a factorial design is ideal, and the real downside to a factorial design is that it's going to really increase the number of participants that you need, and it also makes the statistical modeling of your results more complex. We next consider our options for how participants are exposed to the different combinations of factors and levels. The two sort of ends of this spectrum, the two extremes, are a between participants design and a within participants design. And in a between participants design, each participant is exposed to only one combination of factors and levels. In a within participants design, a fully within participants design, all participants are exposed to all levels. So if you take, for example, an experiment where you have two levels and each factor has if you have two factors and each factor has two levels, you have a 2x2 design. So you have 4 potential combinations there. To do fully within, every participant would go through your experiment 4 times. The downside to this is that you're going to run the risk of creating bias based on transfer effects and demand characteristics. And transfer effects are that as your participants complete the experiment, they start to learn. So the experiments that take place later on, they're going to sort of get the process down and perform better later on. The way to sort of mitigate this a bit is to randomize your order of how each participant completes the different scenarios. Within participants design is, well, all experiments are subject to demand characteristics, but it's going to be especially prevalent in a within participants design. And demand characteristics are where the participant starts to formulate an interpretation of what the researcher is looking at. And then they'll subconsciously modify their behavior in order to match what they believe the researcher is looking for. And as you can tell with the within participants, they're going to be exposed to stuff for a greater amount of time, and that's going to give them more time to create those perceptions. The strength of within participants is that it addresses the greatest source of variance within any experiment, and that is differences across participants. So when each participant when each participant is completing each scenario, then you have a sort of a baseline for everyone, or for each one. So the best solution is to use a mixed model design. This allows you to say, we don't think this factor is going to have any sort of transfer effects, so let's have every participant do both levels here, or this level is particularly subject to transfer effects, so we only want participants doing that once. And so we can kind of pull from both sides and pick some place in the middle that allows us to draw on the strengths of both. For our experiment, we only had one factor that left us with only one choice to have a simple design, and we chose to do a between participants design. We felt that our experiment was highly subject to demand characteristics. Asking people to use tools that may be familiar to them or using our software is going to, if they did that twice, that certainly might affect the way that they respond to questionnaires, because they'll be able to formulate an opinion that, oh, well, they're actually testing this software, so that might affect the way that they provide feedback. So in order to sort of offset this, offset the lack of statistical strength of a between participants, we decided to just take a large sample instead. As I mentioned so this provided us then with two groups, participants that used ICE and participants that used the alternative tools. The next step is to consider how we recruit participants and who we include in our study. And your participant pool should really reflect what you've outlined in your hypothesis, as well as the population to which you wish to generalize your results. Another thing to consider in this step is how you're going to approach these people. How are you going to draw people in to get them to participate? For our study, we wanted to generalize our results to all users and cast a wide net and sample from anybody who we could get to participate. And we found that we didn't want to limit ourselves at all. We're seeking a very large participant pool. We wanted to get 60 total participants. And in order to do that from the population that we had access to, we realized that was going to be difficult, so we didn't want to create any limitations for ourselves. For the most part, the people that we've gotten to participate are scientific professionals that work at the lab with us, and some university students at a nearby college. In order to recruit these people, the best method that we've found for drawing people in is we created a Google form and sent that out to mailing lists and allowed people to respond back and provide their information to us, and then contact and schedule them through that. The next step, we kind of start thinking about how we're going to execute our study. And we consider our experimental task, what the participants do, and our experimental procedure, which defines the environment where the participants complete the experiment, as well as the actions of the researchers during the study. Recording this stuff in great detail is very important for if you intend to publish your results in some way. And the reason for that is reproducibility. You should have a sufficient level of detail on what the participants did and what you did, so that someone could take that, complete the same experiment, and produce non-statistically significantly different results. The experimental task should provide a reasonable level of context, both socially and cognitively. It should strive to reflect the real world as much as possible. And one of the greatest points of how to get an experiment to reflect the real world is motivation. In the real world, people are most often motivated to do well at what they're doing just through maybe not self-motivation, but they have their real-world reasons to do well. And in this experiment, there is not necessarily anything pushing them to do well. So in your task design, you need to consider ways in which you'll motivate your participants, and that motivation can, as closely as possible, reflect real-world motivations. Recording the testing procedure is a good idea, and then it forces you to think about how you as the researcher behave during testing, and then that provides a certain level of consistency in that you always follow the same procedure with each participant. For our study, starting with our task, we needed to select some sort of simulation code for users to interact with, and we decided to go with a code called NEC 5000, which is a computational fluid dynamics simulator. We had existing tools in ICE for running these simulations, so that made it an easy choice that way. It's also a fairly mature code. It's been around probably since about the mid-'80s, written in Fortran and ported to C. It's open source, it's widely available. Anyone can go get it from a public repository. And although we didn't ask participants to go get it, doing those things seemed like a reasonable task for most people. The NEC 5000 project has a moderate level of documentation that someone who wanted to do computational fluid dynamics simulations could easily go get this code. All participants used as similar as possible desktop computers to complete this. Everyone had a single 24-inch monitor. Every machine was running Windows 7. It was just a standard mouse and keyboard. Both groups were guided through a series of similar tasks that replicated or that matched what ICE allows them to do. So each participant, regardless of whether they're using ICE or using the alternative tools, connected to a remote machine, modified an input file, launched the simulation, and then analyzed the output. We didn't have any sort of explicit motivation in ours. We relied on just sort of self-motivation of the participants. By presenting the task as something that was challenging to do, that we felt that would encourage them to do it. We also relied a little bit on reciprocation by giving them coffee and cookies and hoping that we gave you coffee and cookies, so now do well in our study, thanks. Just as a bit of a side note, running the simulation, we set up virtual machines on Amazon's Elastic Cloud computer. So everyone was interacting with essentially this same sort of machine. And if you're interested in more details on that and how we used the Parallel Tools platform in order to get remote connections to Amazon Elastic Cloud from within an Eclipse-based product, come and talk to me about that, and I can sort of direct you to some of our developers that help do that. For our experimental procedure, all participants were initially presented with a consent form to review and sign, and then the researcher, or me, I went through a scripted set of instructions so that every participant was exposed to the same set of instructions. Each participant was given an equivalent user guide for either using ICE or using the alternative tools. And I say equivalent in that the amount of text and graphics in those two user manuals was approximately equal. The testing was administered by a product called Moray that records both the user's desktop and uses a webcam directed at them to record their behavior. The Moray software is a nice piece of software. Unfortunately, it's not open source. It's expensive to license, and it's not cross-platform, which are three of probably my top 5 reasons why I wouldn't use a piece of software. But in this case, Moray was available at the facilities that we were using, so we just went ahead and used it. But recording the desktop and recording the participant are things that certainly you could replicate with open source tools or find an alternative that was within your budget. The next step is to consider what we measure in our study. And in this, we seek to answer the question, how do we capture the ways in which our factors, how do we capture the ways in which different factors and levels affect response variables? And there are 3 different categories of measures that we can take: objective measures, subjective measures, and behavioral measures. Objective measures are those that are quantified through observation. They're highly reliable. Examples of these could be things that you can time, things that you can count, sort of a fact recall from participants of what they, certain information that was presented to them during the experiment. Subjective measures seek to capture participants' feelings and emotions about, or thoughts and feelings and emotions about the experiment. And behavioral measures seek to capture things like verbal and nonverbal and psychophysical cues. And this could be thought of, behavioral measures are sort of an objective measure, but great care needs to be taken in order to validate them, because for the most part, behavioral measures are evaluated based on some sort of researcher's interpretations of someone's behavior, and validating that requires multiple researchers to interpret that behavior and determine that their interpretations are not statistically different. Ideally, you'll use all three types of measures. For our experiment, I'll once again bring back our primary factor of use of Eclipse ICE and our response variables that I mentioned before, which were user efficiency, user success, and user evaluations of usability. So for user efficiency, we said efficiency is measured based on time. So we capture timing data from our recordings. User success, we say, is based on their ability to accurately complete a study, or accurately complete the tasks in the study, which we had several steps in it, and there were a certain level of safeguards to allow someone to not be stopped somewhere by incorrectly completing a step. So we say they successfully completed if they didn't hit those sort of safeguard points, and were able to successfully complete the tasks. Also successfully complete them on their own. They didn't prompt the researcher to ask for help on completing them. So we kept account of times that the researcher had to provide some sort of intervention in order to help them along. For user evaluations of usability, we presented participants with 2 questionnaires at the end. We used the system usability study developed by John Brooks in 1986, and the NASA task load index. We could have developed our own questionnaires and validated them, but both the system usability scale and the NASA task load index are well-established questionnaires. So we felt that using them saved us a bit of time. So finally, going through all these steps and carrying out our study, what has usability testing done for us? How has it affected our project, or how has it affected the Eclipse ICE product? Each participant took about 40 minutes to complete this, so 60 participants. The testing is currently still ongoing, but by the end of, if we can reach our goal of 60 participants, we'll be left with approximately 40 hours worth of video, which is quite a lot of data to look at, but it's 40 hours of people using your software, and to directly see where they're using this. And we hope to use this to, as I mentioned earlier, identify difficult tasks and refactor our user interface in order to mitigate those a bit and increase help text in certain areas. Currently, prior to doing the study, our UI design was primarily done by developer intuition and user feedback. We had no sort of formal design process. The data that we've collected, both the objective data, the timing data, and user responses, provides us with a direct comparison to the command line tools and visualization tools that we provide an alternative to. So we can create a direct comparison and say, we built this product to replace these. How do we compare? For statistical analysis of our numerical for statistical analysis of our results, we used R, which is the statistical programming language. You may be familiar with that. If you're interested in ways of interacting with R, there's the StatET project, which is Eclipse-based tools so that you can do R development directly in ICE. There's also, I just found out in a working group meeting on Monday about a project called Architect, which is essentially the StatET project bundled completely together so that you can just go grab that and start programming in R right away without any sort of environment setup that you have to worry about. So I'm looking forward to getting back and testing that out. Our testing also provided us with a lot of user feedback from, for the most part, new users. Most of these people have never used our software before, and it gives us sort of a first impression feedback. It's also been a way to sort of validate our existing concerns with our software as well as uncover some new bugs. You turn a completely new user loose with your software, you'll be really surprised at the places that they'll click and the things that they'll do that you never thought were possible, that you had never thought of previously. So with that, I want to say thank you for sticking around, and I'll open it up for questions at this time. I also provide the encouragement to evaluate this talk and provide me with feedback. So are there any questions? Yeah.
Is the plan, once you've got everything together, and I guess you're going to make some design decisions based on that, is the plan to let those design decisions then flow back into normal development so that you don't have to do the same kind of thing or on the same scale in 2 years again?
Right, yeah.
Does it do lessons learned from it as well?
Yeah, so we hope to take our results and say, we were consistently working in this way before, and that methodology wasn't working for us. We need to, we've got concrete evidence that sort of that design pattern wasn't working for us. And then
let's do the retest, right?
Yeah, and certainly, being a controlled experiment, we had to sort of branch at some point from our repository and say, this is the version we're going to test with. And so things have changed since then. So we've certainly have a new piece of software that has hopefully more usable things, but maybe we can compare. Well, eventually run some new studies as well. But that's sort of the advantage to doing traditional usability testing is to sort of iterate your product along with your participants. Yes.
In the way people manage to use the software, is there big variance? Maybe it was one of the pictures you showed, but do most of the people do exactly the same thing when they look for the return, or is there a big variance?
It depends. It depends also on the software that they're using. I don't want to draw any conclusions on the sort of limited sample size that we have so far because we haven't reached that 60 participants that we want. We're around roughly 20 so far. So on just a third of our sample size. For the most part, most people follow a similar path, but in watching some people complete it, I've seen them just go completely off and not follow the instructions at all and just end up in the weirdest places, and it doesn't necessarily produce good results for us, but at least it's because we don't have necessarily results, we can it's sort of a throw-out case at that point when they get way off. But which I found that the career professional scientists at the lab are the worst about that. You turn them loose with the people who are theoretical physicists and stuff, you turn them loose with a piece of software and they will turn every knob and click every button that they can, and it just, I don't know how some of them end up in the places that they do in the different software tools. But for the most part, we would hope that that our software is leading people on just a single path. But you know, once we get more data and sort of analyze those videos more, that hopefully we'll be able to draw conclusions on that. Is there anything else? All right, well, thanks again for coming, and please evaluate.